Okay, so that continues to apply even after spring break. But rather than talking about that, let's talk a little bit about the midterm. Apurva went over this yesterday. The video is on Canvas. If you have not seen it yet, go ahead and check that out. Went through this. So just want to say a few more things, maybe a little bit more broad comments rather than getting into the specifics of the answers. But in any event, this first question on fire extinguishers, you should not miss because it has the same structure as a bowling problem. Anytime you're dealing with sampling from a finite set, what is left after you take away part of it is you're gonna have to work out the probability distribution from that. So you should not miss that because we did bowling problems like half a dozen times the first part of the semester between the Thursday sessions and the recitation sessions. But there are too many people who miss some of the points on this, and to compound that, too many people missing some of the points on what is essentially a bowling problem who had not asked any questions during the half dozen times we did bowling problems about what it is they don't understand. Now, this also brought in a little stuff from the beta binomial, but we saw that when we talked about the vaccine study. So, this is stuff that we've seen before, or concepts that we've seen before, just applying it in a somewhat new context. But applying something in somewhat new context shouldn't be a problem if you understand sort of the structure of the problem, which, like I said, is like bowling. Now, this is mostly testing your ability to code these sorts of things with dplyr. So simulate from a probability distribution, simulate from another probability distribution that depends on the previous distribution, condition on the observed data. Bayesian's condition on the data, no one else does. That's a fundamental thing that you need to wrap your head around based on what we did in the first. And consequently, if you condition on the data and have a distribution of what you believe the unknowns to be represented or quantified by your prior distribution, then you can obtain a posterior distribution of those unknowns, conditional on the data that you observe, in this case observing 1 out of 3 randomly selected fire extinguishers was defective in this hypothetical. As it turns out, this was not actually part of the midterm, but there was a recent article in 2019, because it's not so recent anymore, recommending the use of this for, testing reliability of products or factory assembly line, something like that, because you don't need to do simulation. The beta binomial prior is conjugate with the hypergeometric likelihood, so that the posterior distribution for the number of defective fire extinguishers remaining in the building is also going to be in the beta binomial family. So that's nice, but you could answer any question you would want just by doing simulations from this process. Don't need to rely on the fact this is actually one of the rare situations where we have conjugacy with discrete unknowns. Hypergeometric distribution is also applicable to poker. What's the probability of getting a flush between your 2 whole cards and 5 in the middle? So you need at least 5 out of 7 to be at the same suit. That can be answered with the hypergeometric distribution. So we saw a little bit about that in the homework problem of poker, which ties into the more general idea of decision theory. How do we use quantitative methods to inform decisions, policy directions, whether we should switch our fire extinguisher supplier after having found 1 out of 3 defective. And decision theory is, sounds simple. Enumerate the possible decisions, specify a utility function, obtain the posterior distribution of whatever you don't know given what you do know, evaluate the expectation of the utility function under each of the possible decisions, weighting by the posterior probability of, the unknowns, and then choosing the decision that has the highest expected utility, or in this case, the lowest expected disutility. Didn't quite have enough information to make a firm recommendation, but you could definitely outline the process. And in a situation like this, given that even though a fire is unlikely, the cost of having a defective fire extinguisher if there was a fire would run in the millions. So we only need a small difference in the reliability between supplier A and supplier B to, justify going with the more reliable supplier of fire extinguishers. This is entirely hypothetical. Haven't actually found 1 out of 3 defective fire extinguishers in this or any other building. But, you could imagine something like this, a process like this, taking place with any sort of safety-related device. Okay. Questions about that first problem? And I should have said, if I hadn't already, the answer key has been up in the GitHub repository for a while. If you pull, you can get that. So second and third question, our second question is about this article in the the Atlantic, website, about a series of articles that have been or are being published in academic journals about to what extent, whether there's been a rise in income inequality in the United States. That is something that a lot of people have taken for granted. There have been a lot of papers published on that. It sort of forms a prior distribution. But if there was new evidence put forward, we want to update our beliefs based on that new evidence. It's sort of the general Bayesian approach to science, mirroring, it was more or less an established fact that mRNA vaccines did not work through 2019, but they were failing by less and less every time they tried something new 30 years prior. So it's not inconceivable that someday they could work. And that day came in February of 2020. By the time the experimental trials were done, should definitely update our beliefs about the effectiveness and the potential for mRNA vaccines. And this sort of thing happens reasonably often in science, whether social or otherwise. You have, a group of people that sort of establishes conventional scientific wisdom on something, and then someone else comes along to challenge the conventional scientific wisdom. And a lot of times those challenges turn out to not be that important, but sometimes they do. Cold fusion has a spectacular record of failure for many decades. But you may have seen recently a group of people at MIT have been working on stuff, and it's not as if they have it yet, but they think they're on the road to it. And so we need, as Bayesians, to say, okay, we're skeptical of that, but we're open-minded enough, for really a lot, to update our beliefs about stuff that we were previously fairly sure about, if there's some actual new evidence. In this case, with the income inequality, it's not so much that there is new evidence, because both sides are essentially working with the same data, but there are different assumptions applied to more or less the same data, and that does yield different conclusions. So that's perhaps something worth thinking about. I think the fact that wealth inequality, there's evidence that that has increased rapidly over the previous decades, and wealth inequality data is actually harder to come by, but it's mostly different than the data that is being talked about here. Wealth inequality is data is in the United States mostly obtained from property tax records and estate tax records, whereas what we're talking about here with income inequality is from income tax records. And for the vast majority of people, most of their income comes from wages. But most of the income inequality, or at least the income inequality that Piketty, Sayas, and Zugman are talking about, is attributable to massive non-wage income by not just the top 1% of the income distribution, but the top 1% of the top 1% of the income distribution. Your Elon Musk and Zuckerberg, people like that. So anyway, rather than you can read the underlying papers if you're interested in this sort of thing, but what I want to focus on here today is, what does this say about the use of Bayesian thinking and methods and estimation in social science more generally? Fisher clearly would have disapproved of all this, or almost all this, except perhaps maybe the part where there's a relatively small people who are randomly selected for their income tax returns to be audited each year. And possibly you could derive the distribution induced by that randomization to do some Fisher frequentist statistics, but the bottom line is there's only like hundreds or maybe 1,000 people each year who are randomly audited, which is not nearly enough to obtain, if you just chose 1,000 tax returns out of a hat, you're only going to get, 1 or 2 that are really from the part of the income distribution that the Berkeley economists are talking about, and that's not nearly enough to be making or sustaining conclusions. And so if you want to pursue this line of inquiry, you have to go beyond what's in the randomization audits data to other things, and then you get into stuff that is fairly clearly subjective. It's not what Fisher wanted science to be. But we've already seen that if you applied what Fisher said about science to poker, you would obtain a poker strategy that is easily beatable by anyone who knows that's a strategy. The easily beatable poker strategy would entail just doing your probability calculations off the deck. So what cards you can see, and then every other card that you can't see has an equal chance of being it. And not conditioning on the betting or the previous play against the opponents, or taking into account that your other opponents are also trying to win money, any of that. That's all subjective. So Fisher would say you should ignore all that, focus only on what we can objectively say the properties are from the randomization, and the deck is randomized due to shuffling, but that would yield an easily beatable strategy if someone at the table is not even conditioning on what the other people are betting. It would be terrible. But you might say, well, that's gambling. That's not science. What Fisher is talking about is science. Well, we've also already seen that Fisher would have rejected Pfizer-BioNTech's application for the mRNA vaccine because they use Bayesian analysis. But you might say, well, yes, Fisher would object to the priors and all that stuff, but if they had done a frequentist analysis like Moderna actually did, they would have rejected the null hypothesis that the vaccine effectiveness is 0.3 in favor of the alternative hypothesis that the vaccine effectiveness is greater than 0.3. And so you would have ended up in the same place approving the mRNA vaccines, whether you take a Bayesian analysis or a frequentist analysis. Now, you might say, well, the Bayesian analysis is a lot richer. We got a posterior distribution of the vaccine effectiveness rather than merely a point estimate, things like that. So you could make an argument for it, but Moderna's application got approved as well. So maybe it's not essential to use Bayesian analysis in the vaccine context. But we've also seen that Fisher's view of science has absolutely nothing to say at all about global warming, which is the most important scientific issue of your lifetimes. Reason for that, we have one observation on the Earth, and nothing is randomized. So what are we going to get a frequentist distribution over induced by randomization that hasn't happened? And Fisher also said, well, it's not just like, if there's no alternative, it quite explicitly said if you can't be objective about something, then you shouldn't say anything at all. And that's not really a useful or constructive view in the context of deciding what it is we should be doing in the present about global warming, even though we can't objectively talk about any of that stuff the same way that we can talk about, what cards are likely to, or what combinations of cards could come up in poker or something like that under hypergeometric distribution. So the fact that Fisher's view is completely inapplicable to the most important scientific problem that we've ever faced seems like it would be reason to question Fisher's overall view toward science. But you might say, well, yeah, global warming is extremely important, but it is kind of an atypical scientific problem. Most scientific problems we don't have an N of 1. So it's possible that Fisher's view of science is sort of generally worthwhile. It's just in this one particularly important case, it isn't. But the N equal 1 thing is not that fundamental. We have lots of situations in science where we have a small number of observations. What makes global warming completely outside the scope of frequentist analysis, or it should be, I mean, plenty of people do, but it makes no sense, is because there's nothing being randomized in the atmosphere. And so frequentist interpretation of probability is inapplicable. And then if you say, well, if randomization is kind of at the heart of the frequentist approach to science, and then consider how rarely in social science we have adequate randomization of anything. So anything relying on historical data, anything involving institutions, anything involving politicians, anything involving candidates, none of that is randomized. We don't randomize who gets to be senator or any of that. And so the frequentist or Fisher's interpretation of probability does not seem to apply to a lot of things in social science that social scientists are interested in. And Fisher would have said, well, social science kind of came into being toward the tail end of Fisher's life. But Fisher would have said social science isn't a science. So why is it that social scientists insist on using maximum likelihood and other things that were largely created by Fisher to do social science when Fisher would say, like, what are you doing? There's no randomization going on here. This is not applicable to anything. And we know that Fisher would, or we have evidence that Fisher would insist on this view that if you can't say something objective, shouldn't say anything at all. Because Fisher said that for many years with regards to the question of should we regulate the tobacco industry. And since there were no experiments being done on people, Fisher said, well, there's not objective evidence that this is causing lung cancer, or that the regulations that were starting to be proposed in the 1950s, 1960s, when there was a very high rate of smoking and whatnot, would they have any effect? Couldn't get evidence for that by Fisher's standards, even though all kinds of public health people subjectively believed, based on their priors and their theories and the evidence that they saw, that it could be that this was a massive public health problem, in which case we might need regulations and so forth. Then Fisher was very vocally opposed to all of that. And so we're left with a situation that if we took Fisher seriously, most of social science would not be applicable to those sorts of methods. And so we'd be left with either face the choice of not saying anything about those things, or saying stuff that is subjective. If you're going to say stuff that is subjective, then you need some method, which is Bayesian is pretty much the only one that is established at all, for managing subjective beliefs about things. And so here we have this debate between the Berkeley economists and the government economists about income inequality. It's representative of a lot of debates that go on within social science, and neither group is being objective, but neither could they possibly be objective. They're having to make some assumptions, and those assumptions are not objective, and that drives a lot of the conclusions. But the conclusions might possibly be better stated if either or anyone in economics were to use the Bayesian approach as opposed to the frequentist stuff that is common in econometrics, even though it's sort of developed in parallel to a lot of the stuff that Fisher was talking about without explicitly relying that much on Fisher's work. So we see that a little bit more in the third problem on predicting presidential elections, where someone who happens to be an economist using a linear regression model to estimate percentage vote for Democratic candidates for president over the past 100 years or so, adjusting conditioning on all kinds of predictors that are fairly standard in the literature. And that is something that can use the same predictors, same outcome, same data, same everything, but adding priors. In this case, could do this with stan GLM. I think it's a little bit easier to do it with stan LM fairly uncontroversial to have a normal prior with the expectation of 50 on the intercept. Almost all two-party theoretical models would predict that, but maybe a small standard deviation around that intercept. Again, this intercept is relative to centered predictors, and so it is the expectation of the outcome given average predictors, not too different from the expectation of the outcome irrespective of the predictors, which, you know, anything around 50, I think, would be pretty reasonable. And so this is the example of stuff that Fisher would say is subjective and yet is not controversial at all. Almost everyone subjectively believes that irrespective of the predictors, the expectation of the outcome would be about 50%. That doesn't make it objective, but the fact that it's not objective doesn't make it wrong. That's kind of where Fisher, I think, went off the deep end, saying, well, everything that is subjective is too likely to be wrong to be, you know, relied on. Stuff like that. Also need a prior, in this case, a standard LM, beta prior on the R squared. That is maybe has less of a theoretical justification than the intercept does, but you know, they seem to have most of the important variables that people can think of being used here. So to the extent you believe these are actually linear relationships, could come up with a rather above average R squared for things in the social sciences, although economics, I think, would tend to have higher values for that than you'd see in sociology or psychology. And you get a posterior distribution whose posterior medians are not too different from that obtained by Fair. And we can use that posterior distribution to do all kinds of other things. Query the model, you know, what would have happened into 2020 if there hadn't been COVID and the economy had performed, you know, similar to how it had been up until 2020, would have put a high probability on Trump winning the Electoral College under that model. We can also get predictions for 2024. To do that, we're going to have to use some point, or better, some distribution for these three economic variables whose values we don't know yet. They'll be determined over the course of this year. G is the growth rate, Z is essentially the inflation rate, and Z is the number of times it exceeds, the growth rate exceeds 3.2%, and P is essentially the inflation rate. So, since those are currently unknown, you don't know what the growth rate is going to be the rest of this year, or the first 3 quarters of this year. No one does, because it's in the future. U.S. government hasn't even come up with its final answer for what growth was in the past, like last quarter of 2023. So we certainly don't know what it's going to be in the future. But the essence of the Bayesian approach to things is if you don't know something, substitute a known probability distribution that reflects what you believe about that. And so we do all that. We get posterior predictions for the 2024 popular vote, whose distribution looks like this. And you might say, Fair might say, that, well, the mode of this is pretty close to the prediction that's given in the article and on Fair's website. But the Bayesian answer at a minimum is much more than that, because we get a whole distribution of this, which essentially makes it clear that given what we know and what we don't know, the popular vote could easily go either way in 2024. And that nuance, I wouldn't really call it nuance, I think that's really the essence of the answer, is lost, or it's not lost, it was never there to begin with. If you just go to FAIR's website and you click on a couple of things and you get back an answer that's 51.42 or something like that. Which, like I said, it's about the mode of this. But what FAIR produces is the expectation of the predictions given that the intercept and the coefficients produced by OLS are correct. Now, maybe you might be interested in the expectation of predictions. But why would you ever want to get the expectation of predictions conditional on the point estimates being the truth? When, there's only been like 25 elections or so in the data set, that's not nearly enough to establish the exact value for many of these coefficients. And that's even before we get into, is it appropriate to put the past 25 presidential elections all together, or the election that happened in 1920, or 1924, does that really still hold for the 2024 election, which is unprecedented in many respects, despite the fact the same two people were the candidates in the previous election. But given how our remaining uncertainty about the coefficients and the intercept, here, totally not certain about a lot of these, most of these. Given that we're not certain about what G and Z and P are going to turn out to be, and perhaps for some other reasons, also we're not sure what the error term is going to be for 2024. We know, or we have an estimate or posterior distribution for what its standard deviation is, but the things that might go into the error term that are not being accounted for by this model, such as, what all is happening in the Middle East, is Biden, too old, other things like that that are not being accounted for in this model going into the error term, and we don't know what the error term is going to be for 2024. So put all those things together and we have not a lot of uncertainty in the sense that we're very sure it's not 30 and we're very sure it's not 70. So we know a lot, but we don't know nearly enough to say with a lot of certainty what is going to happen with this election. Even if we were just talking about the popular vote, when really you need to do this on a state-by-state basis in order to get predictions for electoral votes. And actually had a conversation about that. Economist magazine in 2020 used Stan to come up with its predictions for electoral vote, and they want to do that again in 2024, but they're making some changes in the model that presumably will come out sometime before November, but is using Stan and using stuff that we'll learn about by the time we get to the end of the semester. So I think one of the things that people will say is, well, okay, the middle of this is not too different from what FAIR produced. How bad could FAIR's analysis be, or the frequentist analysis be? Well, it's missing the big point here, which is there's way too much uncertainty for us to say whether this is going to be like 52 or 51, 50, for Biden. Any of those things are readily possible under the model, irrespective of what number FAIR might have on this website right now. So that's a big picture point. But another thing is, I think when people start to learn how to do Bayesian stuff, they're starting with relatively simple models, and this is relatively simple, even though there's a number of predictors and interactions and whatnot. But linear models are fairly simple. And look at the predictions like this, or look at the coefficients like that, and say, well, there's not much difference between these posterior medians and the OLS estimates, so I'll just stick with, frequentist methods of estimation. And I want to emphasize now that this is a characteristic, insofar as it's generally true, that only really holds for simplistic, maybe naively simplistic models. As you get into more complicated models, and unfortunately we only get into that a little bit toward the last weeks of the semester, where you can get noticeable differences between posterior medians and frequentist point estimates. But those more advanced models are what we need to be using to do cutting edge research in social science or other fields. So those differences are coming, but we only get to it in late April. Do we really start to see, things differ? So any questions about any of that? Okay, so let's get back this. One more thing before we get into GLMs is, so we talked the first day about this plot, illustrating that outside of social science and applied statistics, use of Bayesian analysis, purple line here, has gone up, up, up since Markov chain Monte Carlo was introduced to reintroduced to the statistics community in the Journal of American Science Association article that was published in 1990. And at the time, I said, well, you might think there's something about the data in social science data that is different from not social science data, that social science data lends itself to frequentist analysis, and whatever is going on in this purple must be other kinds of data. Well, that's consistent with the plot, but as I tried to say at the time, I don't think that is a good explanation for why Bayesian analysis has become so much more prevalent outside of social science than within it. Because in fact, the opposite is true. The data that we have in social science lend itself more to Bayesian analysis than to frequentist analysis, because much of the data that we have in social science is just as subjective as anyone's beliefs about the parameters in the model. We saw that with GDP, which it gets reported as data, but it's really just the output of a model created by humans and used by the government, which is not objective at all. Doesn't mean it's wrong, although it is wrong in the sense that we know the standard deviation in the estimates is about 0.7, because we have an equally wrong way of estimating it through gross domestic income, which tends to come up with a somewhat different answer. So it gives us a way to estimate those variances. But anyway, much of the data that we have in social science is just as subjective as anyone's beliefs about priors on the parameters. And so if we're going to be taking the subjective view of probability, we might as well have a way to manage our subjective beliefs as given by Bayesian analysis, Bayes' rule, decision theory, etc. Moreover, in the social sciences, in contrast to the agricultural experiments that Fisher spent most of his time doing, very little of the data in the social sciences is randomized explicitly. And so that lends itself more to Bayesian analysis, which conditions on the data rather than frequentness analysis that marginalizes over the randomization. So anyway, I think more accurate explanation for why this purple line is so much different from the social science lines is there's something different about social scientists, social science people, as compared to people who did graduate training in statistics and most likely had required classes in probability and became more comfortable expressing their beliefs about stuff in terms of probability distributions than the typical social scientist is, where they learn how to do regressions, like the type of thing that Fair was talking about, but don't get deeply into any of the fundamental stuff, like probability or social science methodology, things like that. So anyway, I thought I'd bring that up again. So anyway, moving forward, we've emphasized many times, but it can't be emphasized enough, that social scientists, or scientists more generally, need a generative model for the data generating process. What is a generative model? A generative model is one that you can sample randomly from, including, if we're going to take a Bayesian view of data generating process, you got to be able to sample from the distributions of the things that you don't know. And the distributions you choose as those priors reflect what you believe about the unknowns. And then, given what you believe about the unknowns, you can get simulations of the data under the model. So once you have a model and a process that you can sample from, if you also have a very good and general MCMC algorithm, such as the one in Stan, which puts very minimal requirements on the user. You just need to say or really imply what is the numerator of Bayes' rule in log units. Then it can draw from the posterior distribution. And Stan really does not care. It doesn't know, but mostly it just doesn't care what your model is about. Just give me the numerator and log units of Bayes' rule, and it can draw from the posterior distribution of the parameters in that generative model, conditional on data that was ostensibly generated by that process. You can get updated beliefs about those parameters. And so this is actually the most fundamental thing. Can you simulate from a model? And a lot of the confusion in social science is due to not being able to do that. But if you have that, and you have the ability to use a tool like Stan, then you can get the posterior distribution of essentially anything, at least in theory, or a posterior distribution of anything for which the numerator of Bayes' rule is differentiable with respect to that unknowns, because the algorithm in Stan is using gradients and whatnot. So starting this week, we can, tweak the generative process that we got to starting in week 7. That was, purely linear model, continuous outcome, Gaussian errors. Again, like I said, it's about the simplest case of a regression model. We can tweak that generative process to cover cases where the outcome variable is not continuous, or even if it were continuous, not necessarily Gaussian, and these are rather small tweaks. And from Stan's perspective, they're just negligible. It can go ahead and draw from those posterior distributions. And so the generative models we're going to be talking about today, and certainly the rest of March, are going to yield the same likelihood functions that happen to be used by frequentists. So Bayesians can make assumptions that would motivate using those same likelihood functions, but you don't have to. It's not an essential limitation. Like I said, Stan does not care at all what your likelihood function is, just needs to know what it is. But we're going to be talking about some of those tweaks today, and one of the examples we're going to use uses polling data that was taken from November 6, 2012, and if you don't remember 2012, all that clearly, November 6th was the day before the election, primarily between Barack Obama and Mitt Romney. And Google actually conducted a poll. I don't think Google really does much public polling these days, and released the data, which is also a bit rare. Polling companies tend to be a bit possessive about the individual data, but anyway, we get some data. First few rows look like this on various characteristics of the respondent, and the outcome that we're talking about is the question here labeled, who do you want to win, which is either going to be Obama or Romney or possibly missing. And so that I'll push up to, I forgot to push it, but it'll be on the repository tonight. If you call the model.matrix function, give it a formula and a data set, it will produce the X matrix used in a model like this. It's going to drop any rows that are in A on any of these variables and produce a several thousands by whatever number of columns matrix X. We're going to drop the first column, which is going to be a column of ones, because we're going to handle the intercept our way, similar to how we did before the spring break. And we are going to center the predictors, which is most easily done with this sweep function. So subtracting the mean from every column, margin equal 2, to get centered predictors that we're going to use. And the names of those derived from the values. All these variables in here are factors, except for weight, which is not the weight of the person in pounds, but the survey weight, which we're not even going to use. And then, so all of these are essentially dummy variables, indicating, you know, whether the person is between age 45 and 54, et cetera, except they've been centered. So they have exactly two values, but those two values are not 0 and 1 anymore. They're different from each other by 1, but they're. So anyway, we have 16 predictors, or 16 columns of X, at least, derived from these 5 predictors, because these 5 predictors have several levels each. So any questions about what these data are? And they are fairly standard in the polling universe. So the outcome variable, like I said, is who do you want to win the election that was going to be happening tomorrow when the poll was conducted. And so that is a binary outcome variable in the case of two parties. Anybody who said like the green candidate or whatever, let's just treat it as NA. So we really only have 2 possible outcomes, either Obama or Romney. And here is the math notation for a generative model that is similar to the linear models we talked about before spring break, but slightly different, tweaked, for the case where the outcome variable we observe is either 1 or 0, 1 indicating you favor Obama, 0 indicating you favor Romney. So for all in, the observed 1 or 0 that we see, we're going to define that as whether Y star for the nth person is positive. Okay, what's Y star? Well, Y star is defined as the sum of eta and epsilon. Okay, what's epsilon? Well, epsilon is an error term that is either drawn from a standard normal or standard logistic. In frequentist lingo, if the error term is assumed to be drawn from a standard normal, this is said to be a probit model. If it is drawn from a standard logistic distribution, it is said to be a logit model. But frequentists, because their models only depend on the likelihood, those kind of obscure some details that we might want to, or we should get into from a Bayesian perspective in terms of priors on the parameters. And so you still hear Bayesian say this is a probit model, but there's different kinds of probit models depending on what sort of priors you use and what sort of predictors you use. So it's in the probit model family if you use standard normal errors. So that covers epsilon. Let's continue on with eta. So what's eta? Well, we're making the same structure for eta that we did with linear models. We have an intercept. We have coefficients beta that are multiplied by predictors x. There can be capital K such predictors, as is typical for us or with rstanarm. We want to define alpha not as primitive, but as implied by gamma and beta with this structure here. So if you substitute alpha into this and factor that, then we can interpret gamma here as the expectation of eta, which is to say the expectation of y star for a person with average predictors, as opposed to alpha, which is the expectation of eta for a person who all their predictors are 0. It's usually easier to think about a person with all average predictors than it is to think about a person whose predictor is 0, even though that might not make sense. And we can have priors here. I said normal priors. That's totally typical. Doesn't have to be that way. You know, we could have interactions. Didn't in this particular case, but that would be easy to add. So basically, you know, the intercept relative to centered predictors and the coefficients is the same as what we were doing before spring break with the linear models. The business with the alpha and the linear specification here and the centering, that's the same as what we did before spring break. Main thing that's different is the errors are drawn from distributions with no unknown parameters. So before we would have a sigma, it's a standard deviation of the errors. Here, we're fixing the sigma to be exactly 1. And you can, when you lay out the math of this generative model, should immediately see why that is the case. Because if we go up to y star and say, okay, y star is, or y is defined as the event that y star is positive, well, I can multiply y star by any positive number, and then eta would change and epsilon would change, but the fact that y star is greater than 0 would not change. So we have what's known as a multiplicative non-identifiability here, can multiply by any number, and any positive number. So in order to overcome that or circumvent that, we fix the scale of the errors, whether those are standard normal or standard logistic, to be 1, in which case if we were to multiply y star by any positive number, the scale of the errors would no longer be 1. So by fixing the scale of the errors, now we're going to be estimating eta, or really the parameters underlying eta, relative to standard normal errors. And that actually makes things easier from a Bayesian perspective to choose priors on the coefficients and the gamma, because if you fix the errors to have a scale of 1, your coefficients can't be that big. So not this election between Obama and Romney, but the election before in 2008 between Obama and John McCain, that the data that came out in the exit polls after the election showed that, I don't know, I can't remember exactly, but let's just say roughly 40% of white people favored Obama and 60% favored McCain. But among non-white people, particularly among black people, if you change just the race of the voter, leave everything else the same, doesn't even matter what the other values of the predictors are, the probability that a black voter favored Obama was essentially 0.99. So just flipping one variable caused the probability to go from like 0.4 to 0.99. So that's a shift of about 0.6 in log odds space. And if you work that out, the coefficient on the race variable for in the 2008 election would be about 4, which is probably the biggest effect in the history of social science. In terms of, you know, the first major party candidate to be black and to win, in American history against, you know, generic white guy, basically, and John McCain. I mean, Mitt Romney is also even more generic and even more white somehow, but, you know, it was an unprecedented event. No real surprise that there was tremendous disparity in voting by racial groups in the 2008 election, but that's the biggest a coefficient really ever has been in this context. And so if you're thinking, okay, this is somewhere between at most 4, you can fairly easily put a prior on almost anything else, and it's going to have less of an effect on whatever your outcome is than the race of the voter in the 2008 election had on how they voted. So anyway, most of this similar, but a little bit different in the first couple of lines, and now we have y, which we observe, or is observable, just being true or false, 1 or 0. We don't observe y star in the data, but it's part of our model, and particularly economists are fond of interpreting y star as the utility of the nth voter, or the difference in utility of the nth voter between if Obama were to win versus if Romney were to win. But we don't observe utility directly. So we have gamma and we have beta, all of which are going to need priors. Like I said, gamma is the expectation of eta when all the predictors are average. And so one way you can think about prior on eta is by inverting the error term based on what you think the expectation of the outcome is and work backward from there. So if you thought, for example, that your expectation was that Obama would get 55% of the popular vote with maybe a little bit of a standard deviation, you can apply the Q-logis function to 0.55 in a logit model to get the corresponding value of M0, a little bit of a standard deviation around that, and now we're good to go with our prior on sigma, so that if all the centered predictors were 0, our model would be implying the average person has a 0.55 probability of favoring Obama over Romney. And then we need also normal, in this case, priors on the coefficients. Like I said, there are 16 of them, but you can go through them one by one and think about what you think in terms of would they be more likely to favor Obama or Romney. So the first is a dummy variable for whether the respondent is male. Lots of literature and political scientists that men are more favorable toward Republican, women more favorable toward Democratic candidates. This was back in the day where they would do just 2 genders. Nowadays, they'll usually have 3 choices for that, but you know, this was in 2012, so there's only 2. Then you have dummy variables for each of the ages. So I put -1/4 for expectation of the coefficient on male, up from 0 to -1/4 across the 5 age categories. So older voters more likely to favor or oppose Obama, favor Romney. I didn't know suburban. I put as a prior expectation of 0. Urban more likely to favor. This is relative to rural, which implicitly is going to have a negative expectation, so more likely to favor Romney. And then have other things for the income variables. So there's 5 categories there. Assumes that richer people more likely to favor Romney because he's the patron saint of rich people. And then also the last 3 variables for the region in which the person lives. Those in the Northeast and the West more likely to favor a Democratic candidate. Those in the South more likely to favor a Republican candidate. All those things seem fairly reasonable. needs some sort of a standard deviation, so I use the same one for all of them, 0.15, and so for most of these, that standard deviation is going to be on the same magnitude as the expectation. So, you know, weakly informative prior are going to have some shrinkage towards 0. Questions about any of this? Yes?
I actually had a quick question. So with, you have like the urban and the region, is that what like the L, like the N and the L represent here in this case? I just wanted to make sure.
The N and the L.
Oh,
No.
sorry, like the, yeah.
So this is for standard normal,
Oh, okay.
standard logistic,
Oh, never mind.
not
Okay.
northeast.
Oh, yeah,
And L is not even a region, so,
okay.
well, not a region of the United States. Might be a region of some other country.
Yeah, I was just making sure if it was matching the two, but yeah, okay.
All right. So we got priors on either of the parameters. And so now what we want to do is simulate from our priors, make sure the predictions of our model are reasonable. So here, because there are 16 predictors and I wanted to get this all on like 2/3 of a slide, I had to be a little bit clever, which is to say not super explicit about what's going on here. So I use per to map across the different prior means and draw each of those 16 coefficients from a distribution with the corresponding value of m and standard deviation of s. So I do that 1,000 times for each of the 16 coefficients. And so we get priors, it's going to be 1,000 by 16 data frame. Oh, and then I add to it a column where the intercept gamma relative to center predictors is drawn from its normal prior distribution. So there's now 17 columns. And then, as usual, I cross-join the priors with the data. And the thing that's a little bit subtle here, the column names of priors are the same as the column names of x. And so when you do a cross-join and the variables, the names of the variables in the x argument overlap with the names in the y argument, what cross-join does is it adds a .x suffix to the column names here and adds a .y suffix to the column names there. And so that subtlety is basically what I'm doing here to form eta, according to that. So that's going to be gamma plus, I'm going to pick all the variables that end with .x, which is to say the ones that come from priors, and multiply those by all the variables that end with .y, which are the columns of my X matrix. So I'm going to take these 16 columns of parameters and these 16 columns of data and multiply them together, and then row sum across to get a vector, add that to my constant gamma, and now I have eta as I defined it on the previous slide. Draw epsilon in this case from a standard logistic distribution, so this is a logit model. Define epsilon, add eta to epsilon to define y star, and then ask whether y star is positive. That forms my predictions. I didn't even need that ungrouped statement because it wasn't grouped in the first place, but it doesn't hurt. And then I can see I have like 6 million predictions, so 1,000 for every person in the data, and there's a lot of people in the data, so this comes out to be 6 million. See the first 6 here, eta, epsilon, those added together yield y star. When y star is positive, we're predicting the outcome to be true. When it's negative, we're predicting it to be false. True corresponds to Obama, false corresponds to Trump. Questions about what I did here? Yep. All right. So after we obtain the predictions, we need to see whether they're reasonable. Now, the kind of challenging thing about these binary models is because the outcome is just 1 or 0, it's hard to tell anything from that because you just get a whole bunch of 1s and a whole bunch of 0s, and there's nothing really to distinguish those. And so for assessing whether these things are reasonable, we might instead want to plot the predictions of y star rather than the predictions of y, utility for the difference between Obama and Romney rather than the observable vote. And so here we get a distribution of utility. It is slightly centered to the right of 0, which means slight preference for Obama. Mostly attributable to the fact that gamma, we slid a little bit in favor of Obama because he was the incumbent. So put a prior probability of 0.55 on someone voting, or the average person voting for Obama. So anyway, get something like that. Seems pretty reasonable, but again, this is a plot of y star. And y star is not observable, so it's hard to say whether something that's not observable is reasonable, although this looks, it doesn't go off to like 100 or anything like that. So in order to proceed, we now need to, rstanarm kind of does this for you, say, well, what is the probability of observing y equal 1, y equal 0, whatever, under this process, given the x's and our priors and whatnot. So that would be, the whole thing would be for, what's the numerator of Bayes' rule, but we're gonna focus just on the log likelihood part of the numerator of Bayes' rule. The logarithm of the prior PDFs is very similar, identical really, to what we were doing before, so we don't need to talk about that more. So the log likelihood function, again, log likelihood function is a function of the parameters, gamma and beta, although it is evaluated at the observed y. So that's the logarithm of the product of the Bernoulli probability mass function taken to be a function of gamma and beta rather than y. So we get our Bernoulli probability mass function here. Take the logarithm of that product, it becomes a sum of logarithms, so the exponents come down. Remember, y is either 1 or 0, so we're either this is 0 and that's 1, or that's 0 and that's 1. The log of the probability that y is 1, and then another term for the log of the probability, 1 minus the probability that y is 1, which is to say the probability that y is 0. And so if we define mu sub n to be the logarithm of the probability that y equals 1, which is to say favors Obama, probability that y is 1 is the probability that eta plus epsilon is greater than 0 in our generative model, which if we put eta on the other side of this inequality is equivalent to saying what's the probability that epsilon is greater than negative eta, which is also equivalent, if we multiply both sides by -1, to saying what's the probability that epsilon is less than or equal to positive or not negative eta. And that is in the form of a CDF. And if we assume that the errors are either standard normal or standard logistic, then we need to be using the corresponding CDF of the standard normal or standard logistic distribution to evaluate the probability that epsilon is less than or equal to eta, and thereby the probability that y is 1. And like I said, in this case, I chose to use the logistic, and that's in part because the logistic CDF is a relatively simple and elementary function, given by that there. So 1 divided by 1 plus epsilon raised to the power of negative eta. That's the standard logistic CDF. So altogether, the log likelihood of a Bernoulli logit model is this expression here, substituting that in for the probability that y is 1, and then 1 minus that, it comes out to that other term for the probability of favoring Romney, where eta is again given by this expression involving gamma and the betas. And in particular, in a logistic model, eta can be interpreted, if you work out the math, as the logarithm of the probability of favoring Obama to the probability of favoring Romney. And so this is that's the odds of favoring Obama, and the logarithm of it is the log odds. So one interpretation of eta in a logistic model is the logarithm of the odds for y equal 1 relative to y equal 0. But either way you interpret it, here is the log likelihood function for the process that we just got through simulating. And so once you know, once Stan knows the log likelihood and the logarithm of the prior PDFs, in this case the word normal that we need to use, Stan is good to go. And so, before we go and do stuff with Stan, we can alternatively plot the density of the predictions by plugging eta into the standard logistic CDF. And now we're plotting the probability of voters favoring Obama, which is in more interpretable units than utility. So before we had a plot of y star, now we have a plot of mu, or the probability that y is 1 given eta and the person's x's and all that. And so again, we have something that is a little bit to the right of 0.5, based mostly on our prior distribution on gamma, I think slightly more than half. Voters are going to favor Obama over Romney. And we were reasonably sure about this the day before the election, but our prior uncertainty here, I would say, is not crazy, but it's certainly more uncertain than what people actually thought they were on the eve of the 2012 election. By the time November of 2012 around, most people thought the election was sort of a foregone conclusion that Obama would be reelected. Here, we're putting a little bit of probability, at least, on Obama getting less than 30%, which is not something that anybody thought was plausible, like, during the campaign. At no point in the campaign was that plausible. So, our priors on the betas have implied maybe too much uncertainty in the predictions. Not a crazy amount of uncertainty, but maybe a little bit too much. And you will see this a lot in Logit and Probit style models, that usually what you think are like weakly informative priors actually imply very weakly informative predictions. And you can really tighten up your priors on a lot of the parameters and get even more reasonable predictions if you go to the effort to actually plot what your predictions are and seeing like, oh, this is more uncertainty than what I really have here. All right? Questions? Okay. So, as I said, Stan is good to go. Define a binary outcome. In this case, 1 to win is a factor, so I just make it equal to a logical thing, whether it's equal to the first value, which is Obama. Put in my predictors. I have to specify family as binomial. So we said this was Bernoulli, but Bernoulli is a special case of binomial with a size of 1. R actually doesn't have a Bernoulli in it, it just has binomial, but that can be with size of 1. Specify the link function to be logit, so that's actually the default for binomial, but binomial is not the default family, Gaussian is. So if we have binary data, we need to be explicit about the likelihood we need to use. Specify the data set where all these variables are, same priors that we used in our simulations. Again, M is a vector of size 16. I have 16 different prior means on these 16 different predictors. Yes?
Actually, I kind of have a question. So with like the priors, like let's just say you have like multiple factors. Like, do you just like put that into one prior? Like, especially with the 2020 election, right? We had COVID and like Black Lives Matter and all of those events. Like, you just basically combine them all to like.
Well, you can have separate priors on each of the coefficients.
Okay.
It's just rstanarm requires them all to be in the same family.
Okay, got it.
Which is usually normal, doesn't have to be normal, but
Okay.
most of the examples I will use as normal. But within that, I can give it a vector of m's and a vector of s's if I wanted to. So here I'm doing 16 different members of the normal family for my 16 coefficients, based on the variables that I have. And get the posterior distribution back, like it said. It's often better to plot these because that gives a better sense that this is actually a distribution rather than any particular number. Keep in mind, again, as was the case 2 weeks ago, the intercept and the output pertains to what we've been calling alpha, the expectation of eta when all the predictors are 0. Even though we put the prior on gamma, you don't get back posterior jaws of gamma, even though that was part of the prior, and that is for compatibility with the GLM function, which defines the intercepts relative to the raw predictors, rather than the center predictors, but it's a linear transformation, so you can go from one to the other, and that's what rstanarm does when it brings back the output. So we get marginal posterior distribution for each of these 16 coefficients. These are not independent of each other, but we're not seeing the correlations in the 16-dimensional distribution here. We're just seeing their margins. Most of these seem to make sense. Men more likely to favor Romney in the posterior distribution. Age, younger people more likely to favor Obama. Older people more likely to favor Romney for some reason. Urban, much more likely to favor Obama. The other places, suburban, less so. Income, again, we see not much actually going on here. So, I mean, some of these coefficients are kind of on one side of the 0 or another, but that's kind of one of the things that it's been a bit of a challenge to political scientists in recent electoral cycles. Like, historically speaking, the income of the voter is, rather strongly associated with favoring a Republican candidate, with poorer people favoring Democratic candidates. With Obama onward, that has become less salient relative to more cultural issues stuff, and so we're already starting to see that with these here, and then the South more likely to favor Romney, etc. So pretty much all you need can be seen, or not all you need, but the basics of what you need can be seen with plots like these of the posterior margins. Again, similar to what we did with linear models. Just need to keep in mind the units here are in the units of eta. So the log of odds of favoring Obama over Romney. Keep that in mind. Okay, questions about any of that? All right. So that was with a Bernoulli model. We could tweak this just a little bit to the case where we have, let's say, capital J groups and lowercase j indexes what group the person or unit of observation is in. And then we can get the sum of the yi's for all i's in group J to be y sub j. So assuming all the y's have the same eta, which is often the case in political science, we can aggregate from Bernoulli to binomial. Remember, we defined the binomial distribution as the sum of some fixed number of Bernoulli random variables that all have the same probability. So if everyone in group J has the same eta, then they're going to have the same probability of the outcome, and we can aggregate from Bernoulli to binomial. And that corresponds to a group by operation in dplyr syntax. Since all of these are factor variables and become dummy variables in our model, the intersection of them forms groups. And within each group of men age, whatever, that live in rural areas that have income of, 40,000 to 50,000 and live in the South or whatever, that forms a group of people. Under the model, all have the same probability of voting for Obama or more likely Romney. And so we do the group by and the summarize to get grouped data. And you might notice that there's 6,000 individual observations in the data set, but they fall into 516 groups. And so the first order thing of doing this is, well, you reduce the number of observations, makes things go faster, and it can do the computations quicker. Haven't even changed any of the assumptions. We have the same probability of someone in each of these groups favoring Obama as they were before, but we've now just aggregated it to the group level rather than thinking about the individual level. Groups defined by the intersection of these demographic variables. But the second order thing, which is actually more important, is that it's easier to do diagnostics if you aggregate up to the groups level when possible than it is to do diagnostics on individual Bernoullis, because like I said, they're just ones and zeros and they overlap with each other. You can't really see what's going on too well with that. And so to specify a binomial model, we need to bind together the count for favoring Obama and the count for favoring Romney within each of those 500 whatever groups. The rest of the stuff is the same, except I changed the link to be probit rather than logit, just to show how this would be done. Like I said, you can do this either way, and usually it doesn't make too much of a difference. Usually speaking, coefficients in a probit model are about 1.6 times what they would be in a logit model. So I take all my prior stuff and multiply it by 1.6. Then I can estimate this. Change here, I use the grouped data set rather than the individual level data set to do this. And like I said, this goes faster, but more importantly, we can do some posterior predictive checks. We'll talk more about this next week, but these turn out better, or they're easier to look at if you do this at the group level than at the individual level. So these things are like 90 or 95% intervals or whatever. Each dot is a group. And so the difference between the predicted proportion of people in each group favoring Obama versus what actually they said, with, like I said, 90% or 95%, something bars around that, look like we're doing pretty good. These are 3 realizations from the posterior distribution, which is all I could fit on one slide, but you can look at more of them. But basically just 10% of your dots should be outside these intervals, and it looks like, that's roughly what seems to be happening. So it seems like this model is perhaps fitting decently well. Right? But if we just had the ones and zeros, then it would have been harder to tell. Okay, so that brings us to various functions in rstanarm that start with posterior underscore. We use one of them already on the midterm and whatnot for posterior predict, but there are some others that do different things, but nonetheless create a lot of confusion among people who are just starting to learn how to use them. So the first doesn't start with posterior, but it is related to the posterior. As dot matrix, as dot data frame, as underscore tibble, these are all similar. These are going to return an R by parameters matrix, where the first column is going to contain draws of gamma, and the subsequent columns are going to contain draws of beta. If there were other parameters like sigma or whatever, they would be over on the far right. So this is an R by parameters matrix or tibble or whatever. So it's going to have numbers in it corresponding to each of the parameters, and it's going to have by default 4,000 rows or whatever R is if we do 1,000 draws for 4 chains after warm up, whatever. Okay, so that is what yields posterior draws of the parameters as produced by staining. Then we have the posterior underscore linpred function, which is going to return a R, which by default is 4,000, by n, where n is the number of observations in the data set after you throw away the NAs, matrix where the nth column contains draws from the posterior distribution of the so-called linear predictor, eta, which is the weighted sum of the x's weighted by the draws of beta, and then also the draws of alpha get added on there. So the posterior distribution of alpha and beta implies a posterior distribution of eta for each observation in new data, but if new data by default is the same as old data, in which case you get it back for the original observations. And so posterior underscore linpred returns posterior distribution of the so-called linear predictor in a generalized linear model as estimated by Stan GLM. That brings us to posterior underscore epred, which is going to return a matrix of the same dimensions, but is different because the nth column produced by posterior epred is going to take posterior draws of the expectation of the outcome given x, which is obtained by applying the so-called inverse link function to the draws of eta. In the case of a logistic distribution, it would be applying the logistic CDF to eta. In the case of a probit model, it would be applying the standard normal CDF to eta to get back something that's on the 0-1 space and can be interpreted as a probability, which is the expectation of a binary outcome. Or at least it would be in the Bernoulli case. In the binomial case, the expectation is going to be n times the probability. So the expected number of people in this stratum who are expected to vote for Obama. Anyway, this is by applying the so-called inverse link function. Why is it called inverse link function? Because Fisher and the frequentists called it that, and they do everything backwards. So from the Bayesian perspective, this is really the forward function mapping eta to mu. But because frequentists do everything backward, they think about the link function as mapping mu to eta, in which case the function mapping eta to mu must be the inverse link function. But the inverse link function is the standard normal CDF or the standard normal or standard logistic CDF in this case. So you can just refer to the CDF and not worry about whether that is inverse or forward. And then finally, posterior predict returns a matrix, R by n, where the nth column contains the predicted draws of the outcome given their expectation. As I've emphasized many times, when Bayesians predict something, that means the prediction, it has to be in the same sample space as the thing that you are predicting. And so predictions from a logit-progit model are zeros and ones. Now, we don't just predict once to produce 1 0 or 1. We're doing this like 4,000 times for each observation, so we get a distribution of the zeros and ones. But if you have a utility function or something that depends on the predicted outcomes, the zeros and ones, then you need predictions of that. Other people who are not Bayesians will use the word prediction for things that are not even in the right sample space. That happened with fair, although because it was normal and Gaussian and linear and whatever, it actually was in the right sample space. But what Fair calls a prediction from a Bayesian's perspective, that's the expectation of the predictions, but it's expectation of predictions given that your OLS point estimates are correct, which is not something that we want to condition on. Because the posterior predict in the Bayesian case returns this matrix, the posterior uncertainty remaining in gamma and beta gets propagated through to posterior uncertainty in eta, and then you apply the inverse link function to eta to get mu, so the uncertainty in eta is going to get pushed through to uncertainty in mu, and also uncertainty in mu and also uncertainty about what the epsilon is going to drive variability in the predictions. And so that all gets preserved if you do it the Bayesian way, and you just need to choose which of these functions you need to be using in any particular situation. Which requires you know what the differences between these four functions are. But they're rather fundamental differences, even though the matrix of output is going to have the same sizes in most of these cases. So keep that in mind. So this poll, although it was taken the day before the election, it was a Google poll, so it was done online. And so it had no ability, and it didn't even try to be representative of voters. Rather, it was a poll that was intended to be representative of all U.S. adults, irrespective of whether they're going to vote or even irrespective of whether they're eligible to vote. And it's not even that representative of adults. No online poll is. There's also a lot of missingness, etc. And so one thing that can and should be done with Bayesian analysis is to use what's called post-stratification, which is something that Andrew Gelman has been harping on for many years, which is actually really simple if you know what the population you're trying to make inferences about is. In this case, the population of adults and who they favor, not necessarily voters and who they favor. That was also one reason why I put the prior on Gamma to be favoring Obama maybe a little bit more than what you might think for voters, because almost everyone thinks that adults who are non-voters, if they were to vote or if they could vote, would favor Obama fairly significantly compared to Romney. Anyway, so if we use the expand grid function in the Tayyar package to make a tibble with 864 rows, which comes from the intersection of the levels of each of these variables, and pass that to posterior linpred, we get a 4,000 by 864 matrix. So 4,000 draws for each of 864 kinds of people. Apply the inverse link function, in this case normal, to that. Get 4,000 by 864 draws of mu. And under the assumption that the people we have are representative of their age and gender, etc., not necessarily that the data that we have is representative in the right proportions compared to the population, but just that the people that we have who have like middle income or whatever behave like middle income people in the population of adults. Then we can do what's known as post-stratification. If you go to like the census or the website that has projections updating the census, and get the count of the number of adults in each of these 864 strata. So the number of people who are female and like 25 and live in cities and have income of, $40,000 in the Northeast, whatever, that count number of people you can get from the census. And then if you take this 4,000 by 864 matrix of mu's, so 4,000 posterior draws 864 types of adults, post multiply it in the matrix vector sense by the number of adults in each of those 864 groups. We're left with a 4,000 by 1 or a 4,000 size column vector with predictions for the expected number of adults in the country who would favor Obama, marginalized over the 864 groups. And so this is what is known as post-stratification estimate of the posterior probability for posterior distribution for the number of adults who favor Obama over Romney. And so, like I said, this is rather easy to do if you know what your population is. So the population of adults is a fairly well-defined thing, and we just got through in 2012 estimating it in the 2010 census, and so we can be fairly sure how many of the 864 types of people that there are. It is harder to do, although it's conceptually the same process, if you wanted to make inference about the population of voters, but you would need some sort of assumption or a distribution as to how many people in these 864 four buckets are going to vote. So that's different than are they just an adult who lives in the United States. And so because that's not known until after the election happens, if you're doing this before the election, there's an additional layer of uncertainty there, which is actually extraordinarily important. But it's analogous to the thing that we did with Fair's model on the midterm. We had to put in a distribution for the G and the P and the Z or whatever they were called, because we didn't know exactly what those would turn out to be. If we want to make inferences about voters, we're going to have to make assumptions about how many of people are going to vote in each of these 864 types of people. And that's requires stronger assumptions than merely making inferences about adults. But it's the same process, just with the added distribution here on who the voters are. So you'll see that in terms of talking about post-stratification or regression and post-stratification. All right. Last thing that we're going to do, I have just enough time, is a model on views of videos on YouTube. So views is the number of times. We have 50 videos in this data set, which is a data set of videos about scoliosis, which is probably not the most exciting thing to watch about. How often those have been viewed on YouTube. SCOL is some measure of the scientific accuracy of the video, as rated by like an actual spine doctor or something like that. And then age 2 is the number of days that the video has been on YouTube, among other variables, but we're going to focus on SCOL, and the hypothesis, research hypothesis being considered here are more accurate videos more likely or less likely to be watched on YouTube. And we learned before about the Poisson distribution. It's the limit of a binomial as the number of trials goes to infinity. So the number of opportunities to watch the video goes to infinity across the whole world, which is, you know, reasonable, approximating like 10 billion is infinity, 10 billion people, while the expected count remains fixed and finite. Actually, the same person could watch the video on scoliosis multiple times. So anyway, even more than 10 billion potential watchers of these videos. And so the math for this generative model, so y is going to be a count, non-negative integer. We're assuming it to be drawn from a Poisson distribution whose expectation is mu times epsilon. Okay, what's epsilon? Epsilon is drawn from a gamma distribution with both shape and rate equal to phi. What's phi? Phi is drawn from an exponential distribution with a rate of r. So the expectation of phi is the reciprocal of r. So this is somewhat similar to what we did before spring break. Mu here, which gets multiplied by epsilon. So this is different from like an OLS or a linear model, and that the error term is multiplicative rather than additive. But mu here is e raised to the power eta. So you can also think about the logarithm of e as being additive to eta, and then it gets converted when you do the anti-log business here. Eta is much the same as we've been doing before, with the additional possibility of a so-called offset variable, which enters into eta without a coefficient, or with the coefficient fixed to be 1. Offset variables are often used in count models to change the units of mu to number of views, in this case, per day. So the offset variable we're going to use is the number of days that the video has been on YouTube. Obviously, videos that have been sitting on YouTube longer are going to naturally generate more views. But the rate we're focused on modeling here is how many times is the video viewed per day, which is a more natural metric when thinking about videos on YouTube. Can have normal priors on gamma and beta, again, gamma interpreted relative to centered predictors. Now the thing about these count models is the inverse link function here mapping eta to mu, or what Bayesians would just call the forward mapping from eta to mu, is the anti-log function. And so as eta gets to be only slightly positive, mu gets super big, super rapid. So this is another situation in which your coefficients in a count model with a exponential inverse link function can't be too big. Because like if eta were like 10, e to the 10 is like really big number for the expected number of views of an extremely boring video. So if eta can't really be greater than 10, then there's a limit to how big beta or gamma can be. And you need to have an informative prior, especially on gamma, to get this, somewhere reasonable territory. So the code for drawing from the priors looks like this. Here I've constructed alpha explicitly, cross-join the priors with the data, do my construction for eta using the logarithm of the number of days as the offset variable, my coefficient multiplied by the scientific accuracy of the video gives me eta. I antilog eta to get mu, draw epsilon from a gamma distribution with both parameters equal to phi. I drew phi from my exponential prior, and then y is drawn from a Poisson with rate mu times epsilon. So that is a data generating process for a count outcome. We can plot the predictions. Here I've put the predictions in log scale. So most of these are less than 10 to the 10th, which is good because 10 to the 10th is in like Dude Perfect, Baby Shark territory of YouTube videos. Whereas, most scoliosis videos probably well to less, but still could easily have like 10,000 views, but not 10 trillion, probably. And we don't have time to go through it, but the process that we just simulated from implies, if you integrate out the epsilons, a negative binomial log likelihood function for the y's. And so conditional on the epsilons, y is drawn from a Poisson with rate mu times epsilon. If I integrate epsilon out of that, the marginal distribution of y given x is the so-called negative binomial distribution, which we saw before, like homework 1. So how do we do that in rstanarm? You can call it the stan_glm.nb function, or just stan glm with family neg binomial 2. We have a prior on gamma, standard normal prior on each of the betas, prior with the expectation of 10 on phi. Get the posterior draws. We can plot those. Where's my plot? Plot's gone. It looked reasonable. Take my word for it. Let me run it again while I talk about that. Now it's fine. So like I said, the aforementioned fairly reasonable looking posterior distribution of the parameters from a negative binomial model. So again, on the horizontal axis, we're in units of eta. Now, in the case of binary outcome and logit model, we could interpret eta as log odds. In the case of this model, it's just log of expectation of counts. So it doesn't have a special name, but we're still talking about log units. And so for if these were both 0, or if scientific accuracy were 0, then the expected number of views per day would be e to the 4th. So that is like a few hundred, not a few billion. Coefficient on the scientific accuracy, 98% chance that that is negative. So the more accurate the video, less likely it is to be viewed, or the more accurate a video on scoliosis, the less likely the video is to be viewed. Similar for videos on quantitative methodology in the social sciences. That's why I have like 12 subscribers to my YouTube channel. And then this thing here called reciprocal dispersion, that's ours named for phi. So because this is not infinite, we have considerably more dispersion than in a regular Poisson model. So this model here, if phi goes to infinity, then epsilon is going to be concentrated on 1, and so then we're just multiplying it by 1. So regular Poisson, special case as phi goes to infinity, we look at the posterior distribution of phi, doesn't look like infinity, and so we have massive amounts of over-dispersion in videos viewage, even for scoliosis. But anything having to do with social media, honestly, anything having to do with social science, over-dispersion is the norm, not the exception. Finally, we can do stuff with the posterior predictions to ask counterfactual questions, like we did on the midterm, like what if COVID hadn't happened, what would the 2020 election have turned out to be? We could say, well, what if all the videos were as accurate as the most accurate video in the data set? How much more, actually less, would these videos be done? So here we do this is a ratio compared to the actual number of viewage, and most of these numbers are well less than 1. But there's so much uncertainty and there's so much over dispersion that some of these ratios are just randomly greater than 1, meaning there's like a chance that some of these videos would get viewed a lot more if they were more accurate. But for the most part, most videos, if they were more accurate on scoliosis, would get viewed less. And that's kind of central fact about YouTube and social media in general that social scientists need to deal with, is that the worst content gets liked and shared and viral and all that. Anyway, okay, totally out of time now. I will post the next homework tonight. It'll be due in a week. It will have to do with generalized linear models. And we'll have recitation in office hours as usual next week. A lot of people have been asking me questions about the deadline for pass-fail and stuff like that, so I'll hang around after if you want to talk more about that.
Oh, you're staying? You're also gonna? Oh, research seminar.
Yeah.
Oh, no.